Good morning, class. Just a few housekeeping things to take care of. Going to ask that your homework that you had to do last night for homework, there were 10 questions. You had a sheet. Make sure that you have that for tomorrow. And if you didn't get one, make sure that Peer Helper knows or somebody or the substitute and that you get your hands on one. So I think I have a couple up at the front on the podium. I'm going to just quickly check those tomorrow. I think that you found that those are pretty straightforward, so we'll go over that tomorrow. But make sure when you come tomorrow that you're ready to ask questions for what's on your exam. All right, so that's what we're going to be spending time with tomorrow. Also, just a reminder that those that are writing their rewrite for the exponent log test or the log word problems, that is Wednesday at lunchtime. All right, so I think that's everything. If there's any questions, just make sure you leave them for the sub, and then I can look at them at the end of the day and make sure everything's okay for tomorrow morning. All right, we're going to look at just the last little section, and it's just a very short lesson. And what we have here, let's say, is we have a log that's 50 meters long, and we have a frog at one end of it. And a frog begins at this end of the log, and he's going to jump half the distance each time. So on his first jump then, this frog is going to be jumping 25 meters. Now the frog can only jump half the distance each time, so the next jump is half of 25. So 12.5 meters is what the frog jumps. And so on and so on. The question is, in theory, will this frog ever make it to the end of the log? If it can only jump half the distance, will it ever make it to the end? Well, think about it. You can always take half of a number, right? Half of one is a half of a half is a quarter, half of a quarter is an eighth. So there always, in theory, is going to be some number to half, so we can only get half of that distance. Now, what happens though? What do you notice about the jumps? The size of the jumps. They get smaller and smaller and smaller. In reality, right, what's happening is that the distance gets so small. It's infinitesimal. What's that mean? It's so small, it's negligible. It might as well be zero. That frog, as it's jumping half the distance each time, might as well be at the end of that log. So if I was to say, if it could jump indefinitely, could I add up the measure of all its jumps? Well, how far did it jump? It started at the end of this log. I went backwards here. So it started at the beginning of the log, jumped half of the distance, half of the distance, half of the distance, and so on, even though forever and ever and ever, it's almost like it's right at the end of the log. And that log's 50 meters long. So it's jumped 50 meters. Well, what happens if, this was half of a jump. What happens if something's doubled? So here I have one frog and it's doubled. So the next thing I know, I've got two frogs. And then my two frogs, they become four frogs. And my four frogs, they're going to become 8 frogs. And my 8 frogs become 16. And then I have 32 frogs. And then I'm going to have 64 frogs. Am I ever going to be able to add up all these frogs? Because they keep growing and they're growing and growing. I can't add them up. So this shows infinite growth. So there's something special that happens. If my growth factor is less than 1, it's going to approach 0, so I can add that up. It's getting smaller each time. But if my growth factor is bigger than 1, like this doubling of my frogs, the frogs keep multiplying. They get bigger and bigger and bigger. I'm never going to be able to add it up. It's exponential growth. So get out your scribblers, and this is what we're going to look at. It's called infinite geometric series. So we're looking at infinity, right? Infinity and beyond by Light Buzz Year or Buzz Lightyear. Right? What is infinity? Well, there's a quote by a Greek that says, "There is no smallest among the small, and no largest among the large, but always still smaller and something still larger." There's no end. That's what it means. There is no end. So here our exponent is infinity. So our ratio, our growth rate to the exponent of infinity, it means it goes on and on and on and on and so on and so forth. Well, what happens with that is it says this is going to approach 0. That means r to the power of infinity gets closer to 0 if, this is the big one, if that ratio is between -1 and 1. So that means basically that I have a fraction that's there. The absolute value of the ratio is less than 1. Now, there is something else that happens. If that ratio is bigger than 1, then it never stops growing and thus can never be added up. We say that there's no ceiling on it. Ceiling means it's contained. Well, this will never be contained. So these give us, the first one's an example of the frog jumping on the log half of the distance. The other is the frog doubling. So we have two possibilities. We have one that's going to give us an answer, a solution. So we're going to be able to find an answer. And we're going to say it's an estimate because it's not going to be exact, because we say in theory it's going to keep growing minimally, marginally, like just something that word is infinitesimal. So we'll be able to estimate a total. But down here we can never estimate a total. It can never be added up. So in this particular case, what we're going to have for an answer is no sum. So when you see that was an easy one. You say, can't add it up. Impossible. So those are our two situations that we have. So we have just a few examples here. And what we have to look at first is our ratio. Can we identify the ratio that we have? So here's our first example. Oops, sorry. This is just going to show us, first of all, our formula that we have. So in all of these cases, we're going to look at this. If the absolute value of our ratio is less than 1, so we have r to the power infinity. So if that happens, we say that this becomes so small, it might as well be 0. Well, let's put that 0 in. All right, so we might as well say that that's 0. So I'm rewriting this formula. So I put a 0 in. So then I reduce that, all right? So 0 subtract 1 is -1. So a times -1 is -a. The denominator stays the same. This is what we get for our formula. So this is the formula you need to write down. This is for an infinite sum that adds up. The n is infinity. So we have -a over r minus 1. That's the formula we're going to use if the absolute value of r, is less than 1. So we're going to go through some examples. I think there's 3. Example number 1. Find the sum. 128, add 32, add 8, add so on and so on and so on, forever and ever. Amen. Well, first of all, we know some things. So we know the value of our first term. What is it? 128. The r. Now, some people were having trouble finding the ratio yesterday. This is what I suggest. Take the largest number, take 2 numbers, consecutive numbers. So I'm going to take 128, it's larger, divide it by 32, and I get 4. Now, because it's going down, I'm dividing by 4. I'll say that again. Take the larger number of 2 consecutive numbers, divide it by the smaller. In this case, I have 4. So that means my ratio, because I'm getting smaller, is 1 over 4. If it was the other way around, the numbers were getting bigger, it'd mean I'd multiply by 4. Right? Or you could take like your second number, your 32, and divide it by 128, and you're going to get 0.25, which is a quarter. So either way to do it. So I have a and I have r, and what's n? Well, n, in this case, is infinity. That's what those 3 dots mean. They call them ellipses. It means and so on and so on. So here is the key, right here. Is this number less than 1? The absolute value of it less than 1? Yes. So we use our formula. Our formula, negative a over r minus 1. So negative 128 over 4 minus 1. Right, put that in your calculator. So we're taking negative 128 and we're dividing it by 3, and we get negative 42.6 repeating. So if I was to add it up forever as that went, I get negative 42.7, basically. All right, so where's the negatives come in? Well, remember, it's getting smaller and smaller and smaller forever. So that's where the negatives come in here. Okay? That's not very hard using the formula. Let's look at example 2. Example 2, we have 3, 9, 27, 81, and so on. Well, what's our first term? First term's 3. What's the ratio? Well, we're multiplying by 3. 27 divided by 9 is 3. N is infinity. The thing we need to look at is this r. Is this r bigger than 1? It is. The answer, no sum. Why? Because I can't add it up, because it keeps growing and growing and growing forever. I can never add it up. There's no ceiling to it. Bet you like that answer. Remember, it corresponds with our ratio being bigger than 1. And our last example is one of the reasons, what I like actually the most about this, the reason for this is a word problem. Very simple, and they actually happen to do more with ecology or with the environmental studies. So let's copy down this question. All right. The first year that a sugar maple tree is tapped, all right, the first year that a sugar maple tree is tapped, that's this time of the year, it produces 50 liters of sap. As the tree ages, the sap production drops by 4% per year. Find the estimated total amount of sap that the tree can produce. So, let's say this tree lives forever and ever and ever. All right, so it's still going to produce sap, but it's decreasing in its percentage that it yields. But let's say we don't know how long the tree is going to live. For its lifespan, that could be 400 years. Right? Then that's what we're looking at. So we don't know, so we have an infinite series question. So let's look at the information we do know. In its first year, that would be our first term, how much sap does it produce? It produces 50 liters. What is its ratio? Now here's where we have to be careful. The production drops by 4% per year. Now we've done questions like this. This is the one some of you had the most difficulty with. Well, its production rate now is 100%, which is 1. 100%. And it's dropping by 4%, which is 0.04. So its rate of growth is 0.96. All right, so when I have a production, if it's dropping, it's a minus. If it's increasing, it's adding, but we start with that 100%. And we know that this is going to go on for the lifespan of this tree, however long it is, forever and ever. How much sap can this tree produce? Well, we need to look at our ratio. Is the ratio less than 1 or is it greater than 1? It's less than 1. If it's less than 1, then we're going to use our formula. So our formula, negative a over r minus 1. A is 50, so we have negative 50. Our rate of growth is 0.96. Subtract 1. I did this out. See what we have. working that out, you should get 1,250 liters. This particular tree, estimate that that is the total amount of sap that this tree will ever produce. These types of questions are great for estimating mining, right? Production of oil. We know there's only so much there, right? Even though it can still kind of produce at some point in time, it's gonna like basically run dry. Maybe not dry, but almost dry. So dry, so close to being dry that might as well be dry. That's what we're looking at. So there are a few questions in your textbook that cover this. So we're looking at page 120, or sorry, 130. And number 2, it's asking you to do which is an infinite geometric series, or sorry, which infinite geometric series have a sum, and then if you can tell what is the sum. So remember, that's all based on that ratio. If the ratio is less than 1, you can add it up. And then it says determine the sum in questions 3. And number 5 is a little word problem. So number 2, 3, and 5. Okay? So actually you only have to do 5A. And that well will run dry. So this is what I want you to work on. All right? So lots of questions there to do. Answers are in the back of the book. This is a great section out of your text. If you have questions, make sure you have them written down or something for Wednesday, right, for tomorrow, so that I can answer any questions that you have. All right, enjoy the rest of your day.